All right, we have a good case study here in class. This is a 2003 Ford Expedition with a 5.4 liter engine. We have two trouble codes. Well, first of all, history on this car. It was at another garage for misfire problems. I believe they swapped some coils around. They actually cut two of the ignition coil control wires and wired in two different wiring or two different control wires because they thought maybe they had a wiring harness problem. There is a used computer on the floor inside, and so we got the car after all of this. I don't know if they tried swapping the computer. We don't know the full history, but somebody's been here and been playing around. So misfire, we have a constant miss, and the trouble codes that we have in memory, I'll zoom you in on this real quick. We have two codes that we're worried about. We have a PO356, which is ignition coil F, primary / secondary circuit fault, and a PO174 system 2 lean. So, of course, doing a little homework is essential in this case. And if you pull up this 356 trouble code, what you find is coil F is actually cylinder number 6. So the way Ford does these is if you had a ignition coil A circuit fault, that'd be cylinder 1, ignition coil B circuit fault, cylinder number 2, and so on. And so cylinder or coil F is going to be cylinder number 6. So we have a fault with the primary / secondary circuit of that coil. And then we have a 174 code, which is bank 2. Now if you know Fords are numbered. This is a V8, 1, 2, 3, 4 on bank 1, and 5, 6, 7, 8 on bank 2. So cylinder 6 is going to be on bank 2, and so with a misfire on cylinder 6, we're going to ignore this lean condition code for right now. We're going to address the cylinder 6 misfire first. Now that doesn't mean we couldn't have an intake runner or something like that, but you're not going to have a primary secondary fault for an intake runner gasket leak. Our focus is going to go right to this ignition system next. Okay, so this is a coil over plug engine. I've shown a video previously on a Ford coil over plug system with a misfire and where we access the coil primary current ramps from the fuse box. So that was our goal with this one, is we want to do the same thing. We mapped out the coils, and what we found is this one's a little bit different. This one actually does not have a designated fuse for the coils. This up here that we have marked in blue is going to be our power feed for this circuit. The green circuits down below are going to be the separate control wires. Unfortunately, with our power feed, it does go to the fuse box, but inside the fuse box is just a jumper. There's no fuse, and then it goes right to the ignition switch. So the ignition switch directly supplies power to the coils on this design. And so what we did is we actually were able to easily dig that wire out of the main harness that runs down the column for the ignition switch, and that's where we adapted our amp probe for our current ramp measurement. So we'll be able to read all of the coil firings, the current flow on the primary, coming from that wire on the ignition switch. I'll give you a shot of that wire real quick. Okay, I'm under the dash. You see the dark blue with a light green wire is our wire for our ignition coils. I'm using an amp clamp, and it's set on a 20 amp scale. And our 20 amp scale is 100 millivolts per amp. If you were using a voltmeter, we have a scope that does the conversion for us. So that'll be our first channel. We're going to look at all of the coils firing from this location. It's just an easy place to do it, which is why we picked it. Okay, so our first connection, we are connected to the wire that comes out of the ignition switch, where basically in this picture we would be, our amp clamp is right here. So we're going to read all of the coil current firing ramps, coil ramps, from that feed. The only problem with this right now is that each coil is going to obviously fire individually. And so we're not going to know which cylinder is which by this first channel, first connection alone. And so what we're going to do is we're going to synchronize it, as I did in that other video, with one of the primary voltage waveforms. And we're going to pick an easy one to get to, and it's going to be cylinder number 1. Cylinder number 1 in this picture which one is cylinder 1? It's this one right here. So we're going to put a connector, back probe this control wire with our voltmeter part of our scope. We're going to do a voltage waveform on that number 1 cylinder control wire, and so what we'll have is 1 pulse on this signal for every 8 pulses up here, and we'll be able to coordinate them together and take a look at what all of our coils are doing at the same time. So we'll take you up to the board next and show you the waveform. Well, actually, so let me get a shot of where we're connected, and then we'll go and show you what it looks like up on the board. Okay, this is the number 1 coil, and we're connected to the control wire, and we're going to get a voltage waveform on our second channel, and again we're going to synchronize that with our current waveforms on channel 1. Okay, the scope we're going to use for this one is our Pico. Channel A is my amp clamp. Channel B is going to be my coil primary voltage. Now, one of the things you have to be careful of when you're looking at anything that has a collapsing magnetic field is very high voltage spikes. It's not uncommon to see upwards of 400 volts on a primary voltage waveform. So I've put an attenuator in here, and it's a step down by 20 in voltage. And so what that's going to do is protect my scope. This scope has a maximum of 100 volts on this model. This is the 4000 series. And this is going to step it down by 20 so I can safely read much higher voltage without damaging my scope. And so I just have to tell my scope when we go up to the board in the settings, I just have to tell it that I have it in there so I have the right readings on the board. Okay, our settings real quick for this. Channel A, we're using an amp clamp, so I've already changed it to that. Your settings for that would be this. I picked a 60 amp current clamp in the 20 amp mode. And so basically I'm telling my scope what I'm using, so I don't have to worry about converting millivolts to amperage. You can do it both ways. This works fine. So channel A is going to be my amperage. That's going to be my coil firings. Just want to get this as close to 0 as possible. Close enough. And then channel B, I need to tell it what I'm using. Again, I've selected a 20-to-1 attenuator, and what that's going to do is that's going to set my scales up for me. If you look at the scales to the right, you see negative 100, positive 400 volts. It does the conversion for you. The key is on right now. To give you some perspective, you see this is 0 volts here, and this is 50, and that line's not quite at 0 because we're on a coil control wire that's not being grounded yet. So we should have battery voltage on this coil negative control wire. That's exactly what we have in that picture. Looks like we're getting a little bit of noise with the amp clamp, but that's okay. Can you reach inside on the amp clamp and re-zero that for me, Brad? There's a button. Just hit the button once. Did you hit it? We have some kind of a reading coming from that wire right now. There's around, this isn't necessarily a problem, guys, but we have a steady 1 amp of current flow already on this circuit. That may interfere with some of our measurements. Just keep that in mind for what we're looking at. Go ahead and start the car. Okay, this initial first view is not bad at all. We're getting some little bit of connection problems in here. Okay, that looks good. All right, so this is our first view of this. Let's separate these a little bit. Let me pause it there. Go ahead and shut that off for a second. Let's talk about what we're looking at first of all. Fords use what's called a multi-strike discharge ignition system. And so instead of having 1 spike, we actually have 3 spikes if you see them right here. And we'll zoom in on this a little bit more detail later. But this is, for now, that's not important. What we're looking at is this red trace is our number 1 cylinder. So this is our number 1 cylinder control. This is our voltage waveform for the number 1 cylinder. The amp clamp's connected to the ignition switch, so this is all the other coils firing. This is the number 1 again, and this is the number 1 again in this screen. what we need now to figure out where our problem is, which is pretty evident, we have a missing ramp in here. To figure out which cylinder that is and see if that matches our trouble code, we need the firing order. And our firing order is 137 26548. Okay, so we plug our numbers in. 137 26548 and 8. Cylinder number 6 has a missing ramp. That matches our trouble code, our P0356 trouble code, which is ignition coil F, circuit primary secondary. That matches that code, and so that 356 is in fact pointing to cylinder number 6. Cylinder number 6 is where we're going to focus. Now what we know about this so far is there is no amperage occurring during the cylinder number 6 firing event. So with no amperage occurring during cylinder number 6, that doesn't necessarily mean we have a bad computer driver, although that is one option. We could have an open in the circuit somewhere. We need to address cylinder 6 with a voltage pattern, and we'll do that here in a second. As far as detail with this picture, it really isn't necessary to look at these other ones. Our main focus is going to be number 6, but certainly we can look at just that one pattern and get a little bit of a better idea of what you're looking at. This is, again, a primary waveform. And that is a multi-strike discharge system where it fires 3 times. And this is basically a low-speed operating condition. Once you go about 1100 RPM, this goes away and converts back to a conventional single-strike system. So that matches, if we follow our amperage waveform, you can see they go right over top of each other. 3 different amperage ramps occurring same time these voltage waveforms are occurring. The spike is the collapse of a magnetic field, and that would be when the current flow stops. As you can see in this picture, current flow, shut the current off, we get a spike. And there's a lot of stuff we can do with these waveforms, but again, we're not worried about the detail in here right now. Our main concern is this number 6 cylinder that we're missing our ramp. So we're going to address that one next. Okay, as far as attacking this number 6 cylinder, there's a lot of different ways that we can do this. This isn't the only way, but we're using a scope. We're already there. We're going to continue with the scope testing. A little bit of oversight here for this number 6 cylinder. We have a common feed, and this common feed is going to feed all of our coils. So we're not worried about a power feed problem as far as a main power feed. Could we have a break in the power side to that one individual coil? Absolutely. But here's the circuit. It's going to splice and go to all the other coils, but our cylinder 6, you're going to have a coil, and then this other wire is going to go to the engine computer. The computer is going to control this coil negative. What we're concerned about with our cylinder number 6 coil, we are concerned about this feed wire, which is going to be in this section in here. Could we have a break in this feed that's causing our problem? Absolutely. Could we have an open in the coil that's causing our problem? Absolutely. Could we have a open in this control wire between the coil and the computer? Absolutely. So open there, open there, open there. We're not worried about a short necessarily here because our amperage would be high during that section, and these coils are drawing upwards of 8 amps a piece. If this circuit was shorted to ground, this is weird, but what you would see is the exact same pattern, except it wouldn't be at 0, it would be up at 8 amps, and everything would be added to it. We don't think the circuit's shorted, we're dealing with an open. So open circuit tests, what we're going to do, this is the next easiest one. The computer's already open, somebody's been here and already rewired some of the control wires on this car. So we're going to take, and we're going to back probe the PCM on that control wire, and we're going to do a voltage waveform at the computer. Okay, so a little bit of electrical theory there would be if this circuit is off on this design, what are we going to see? What kind of voltage? Our feed voltage engine running is going to be 14. What are we going to see all the way at the computer with the circuit off? We want to see 14 volts. If you see 14 volts at that wire, how's this, how is this, and how is that? It's all good. Okay? The way this circuit should work, if you look at this, take this known good picture. This is the number 1 cylinder. If you look at this pattern to the right, you see 0 volts here. You see around 14 volts on this line. That's what it is. Actually, we can get a measurement there for you for argument purpose. There you go. Around 14.9 volts. My cursor's a little bit high there. Maybe we get the idea. Okay? So this is when the coil is off. And what happens next? When the coil turns on here, let's zoom in on this. What happens next? What is this line? This is battery voltage here. I know we're on the control wire. Right here is where the transistor turns on, right? As soon as that transistor turns on, that voltage is going to drop. That's what we want to see. I mean, we know we're not going to see that on the number 6. But what we have on that number 6 wire is going to tell us whether or not we have an open in the circuit or whether we're going to focus at the computer. If we go to that number 6 control wire at the computer and we read 14 volts, where is our focus going to be on this car? Sorry, truck. Our focus goes to the computer. If we read 0 volts on this control wire at the computer, where does our focus go? Harness, coil. It's an easy check. That's where we're going next. Okay, so we're under the hood, and again, we chose this test because of its ease of use. This is a very easy test to use, and we're going right to the computer. And again, somebody's been here, and they already have done some rewiring. And of course, it's the wire that we're testing that's been, can you pull that clip out of there real quick so I get a shot of that wire? Just pull it. Good. So you can see that somebody has cut this, what's the color of that wire? Orange and yellow? Orange with a yellow tracer? Yes. Our number 6 control wire is orange with a yellow tracer. Somebody has cut the wire and rerouted a new wire to cylinder number 6. Now, if you know how to do voltage measurements, how much time are we going to save here by just looking at a voltmeter reading and saying the harness is good? So that's what we're going to do. Kind of plug that back in. Our voltage measurement at this location is going to be key to our diagnosis. Again, if we see a steady 14 volts on this wire with the engine running, our harness is fine. And if we see a steady 14 volts and the harness is fine, why would you cut the wire and run a new wire? How much time is that you're gonna spend wasting doing that procedure? Take a voltage measurement, see what you have. If we have 0 volts on this wire, then we have to go into the harness further and find out where our problem is. I know these cars are known for bad coils. That is not the case with this car. It's already had coils substituted. It's had wires replaced. They're ready to call a computer. They bring the car to us. That's where we're at. Back to the board. Okay, we're back on the board. We still have our amp clamp connected inside. We're on our control wire for our number 6 cylinder. The key is on right now. Okay, and right away we already see something here. I see voltage on this wire with the key on. The fact that we have 12.3 volts at the computer with the key on is already telling me that this circuit is intact and there's no opens in this circuit. If we had an open in the feed, an open in the coil, an open in the control, this would be 0 volts here. Got to start the car. 12.3 was our battery voltage. We should see this line rise a little bit as the alternator comes into play. showing 15.1, my cursor's off just a little bit. How is our control wire? How's our coil? How's our feed wire? Our focus is now toward this engine computer. Now, one of the things that you need to be careful of when it comes to an engine computer and a transistor is the computer shutting that circuit off intentionally? And from my experience, it does not ever do that with ignition coils. It does that with fuel injectors to protect the cat. In fact, if we check cylinder number 6 injector right now, it's probably not firing. My focus for this video is not to show you that part, but if you think about that, and you started with a fuel injector on the number 6, boy, would that throw you for a loop, because the computer will shut the injectors down to protect the cat. So you have to be careful with that. One of the keys to identifying that, though, is when you shut the car off and restart it, that injector will fire for a few seconds before it shuts down again. And then you can see that it's an intentional shutdown. In our case here, that's not the case. What we need to worry about with this picture is computer powers and grounds before we replace the computer. But if you think about that, is a bad computer ground or bad computer power going to affect one cylinder? Not a chance. I'm going to shut that down. The only other thing that we may want to consider for this, and this might be a reach for this design, but a crank sensor problem. On some model cars, one that I'm thinking of in particular would be a Nissan with an optical distributor and oil in one of the drive plates, blocking that single cylinder. And every time it comes around, the computer never knows that that cylinder is going to fire, and so it never fires it. Before we would replace a computer, we'd probably want to check the crank sensor, cam sensor signals on this car, make sure they look okay. Chances are that's not going to be the case here, but when it comes to a few $100 computer, some of these cars, maybe it's $1,000. I mean, we really want to be $1,000 confident that this thing needs a computer. So we're going to check those variables. One other thing to consider is this circuit right here. If this driver, in fact, did get damaged and got cooked, is it a possibility that cylinder number 6 ignition coil shorted out and caused this condition? So when it comes time to, let's say, replacing this computer, you can be sure that we better be doing some checks on this cylinder number 6 ignition system, or this cylinder number 6 ignition coil. We can do some ohm tests on it. I don't really like the ohm meter for ignition coils, and I'll tell you what I want to do with this is I want to move this cylinder 6 to a different cylinder, one that's functioning right now, and take a coil current ramp pattern of it and see what it looks like. And that's where some of this theory is going to come into play. We'll see where this is going to take us, but if we have to do that, we will. And I got to tell you that I don't like some of these other coils here. And just to show you guys a little bit of insight on this, do you see the straight up line right here on this initial ramp for this one? All right, let's look at some of the other ones. What do you see with that one? Wow. See the oscillation right there? That's a good coil. Let's keep going. Here, let's get some more detail in here first. Let's go. Turn on oscillations. There's a lot of theory involved with these. We'll handle that later, but that's a good looking coil. How's that one look? Next cylinder over. That looks pretty good. Got a nice ramp right here. A little bit differences in the second two. Let's focus on the first one for now. It's a little sensitive, sorry. How's that? Looks pretty good. Go to the next one. So that was 2, that was 3, this will be 4. Okay. Initial turn on ramp. and I'm not counting in firing order here, this is just the 5th one we're looking at. Turn on ramp. So far 5 of those look pretty decent. This is the 6th one, not cylinder 6. A little bit differences in these second 2 for the oscillations, but this one here, that looks good. These coils are known for failing. What you're looking at is some failing coils here. This one in particular, what do we see? What's missing in this picture? And now this is one of the good coils. This is one of the good coils. This is one of the coils that's firing. There is a problem here. There's a secondary problem with this coil. So not only do we have an issue with cylinder 6, which is the empty spot here, the one right before cylinder 6, that should be cylinder number 2 in the firing order, also has a coil issue. Got some major problems here. I think the next step is going to be, let's address that coil number 6 and get a current ramp pattern of that one to see if it's really, really high, and that'll tell me whether or not that cooked this driver. Now sometimes drivers can fail without over amperage, so we'll see what happens. Cylinder 6 current ramp. Okay, what I'm going to do to try to save a little bit of time here, we're not going to do cam and crank signals. We're not going to check computer powers and grounds. Our main concern is this number 6 coil, our number 6 driver. Why is this driver not functioning? In our scenario, what we have so far, 9.9 times out of 10, we have a driver issue. But one of the things we need to be worried about is what cooked the driver. You never want to just replace a computer because a driver failed. You always want to check it. I've done this before on previous cars. We're going to do it on this one. We're going to switch control circuits from another coil. Our firing on this car is 1, 2, 3, 4 on the passenger side and 5, 6, 7, 8 on the driver's side. What we're going to do is take the number 5 control wire. We're going to unplug the number 6, we're going to take the number 5 control wire, and we're going to control the number 6 cylinder with it. So our plug for the number 5, we're going to move to the number 6. We're going to then, at the computer, we're going to use that number 5 driver is actually going to be controlling the number 6 coil. And what that's going to allow me to do is to see the current flow from that number 6. Now some of you might be thinking, well, that's bad because you might damage the number 5 driver, and you're right. But really think about it. Do we care? It's going to need a computer anyway. I want to see what this coil looks like. This will give me the best way to do it. Some of you might want to use an ohm meter, and I'm not saying that that would be a bad idea, but I found a lot of bad coils that show good with the ohm meter because it doesn't stress the circuit. I want to see this coil under stress. This is going to be the best way to do it, and this is going to confirm what we have with this number 6. So on our picture, on our screen up here, we're going to take a look at that. I've changed some settings. I moved my amperage scale to a 20 amp because we're going to see more amperage. Still have my red trace is going to be my number 5 control wire. And we're going to start the car. We may get a little bit of backfire, a little bit of popping, because really we're firing the number 6 at the wrong time. I don't care about that. I'm only going to do it for a second. Go ahead and start this for me, Kevin. Alright, kill it. That's all we needed. So even if it was popping and banging, our main thing, if you look at this picture, if you can see clearly how high the amperage is on this one coil that's on this screen now. Now, of course, we're still missing one, but this one that's missing is the number 5, because the number 5 is unplugged. That was a good coil, right? Our number 5 is unplugged, and so our missing ramp is actually our number 5. This big one is now the number 6. We can't plug our numbers in accurately because we're using the wrong cylinder in the wrong location, but this is actually the voltage on the number 5 control circuit, but what coil are we controlling? It's actually the number 6. This is the number 6 coil current, number 5 control. Look how low these voltage spikes are. Would be the first thing you would notice with this picture. If you look at the red trace, our voltage spikes are only hitting 37 volts. where our good coil, we didn't take a measurement of that, it was a few hundred volts. Why do we have a low voltage spike? Because there's no magnetic field. This coil is shorted. Coils have to have good magnetic fields to make good voltage spikes, big voltage spikes. Look at the amperage waveform, we'll zoom in on that. Pause this for 1 sec, I'm going to save this picture, just in case I lose it. Okay, so what we're going to do is zoom in on this number 6 coil current ramp, take a look at it. You see our other ones, look at the difference between these. You see a good firing coil. Remember, we had actually one bad one in the mix too. But look at this one. Look how high the spikes are and how small the dwell time is. The computer's protecting itself with this right now. That's what's going on in this picture. We have some circuit protection taking place. You take a look at that waveform. We're getting a peak amperage of about 15 amps of current, as opposed to one of our other ones. Try to get an average maybe of 7.7. So almost double the amperage that this number 6 coil is producing. What happened to this number 6 driver? It got cooked. By what? By that shorted coil right there. Should coil current ramps have straight up lines? And in my book I cover this, that a current ramp pattern should never have a straight up line. That is clearly no ramp at all. This is a seriously zoomed in view of this spike. There is no ramp there at all. It is a straight up line. Very small dwell time. Computer's trying to protect itself. We look at this red trace. That is your coil primary voltage on this same circuit. And look at this voltage waveform. It is also a really crappy looking waveform. Is the driver turning on? Yes. Is there good control on this circuit? No. There's really no spike there at all. This is a dead circuit. Really no reason to beat this to death any further. This circuit in this picture really says it all. Number 6 coil that cooked the number 6 driver. This vehicle needs a number 6 coil. It needs an engine computer. And we had another one too. You guys remember what cylinder that was? We didn't like the ramp on that cylinder. Was it the number 5? I thought it was number 2. In our previous picture, we had one other coil that we didn't like on this vehicle. Thought it was a number 2 as well. In any case, we need our main issue, number 6 coil in the engine computer. We do have one other coil. We can go back and look at that part. You know, these are known for bad coils. I'm not saying we need to replace them all, but this is a good example of what you need to do. You have an output that fails and it cooks a driver. You better make sure you check that output. That's where we're at.